All right, so we've talked a little bit about radian angles, and let's expand on that a little bit and start talking about how things rotate and then how that rotation maybe moves an object, right? Like a car or a bicycle. Okay, so first of all, can an angle that we rotate be greater than 360 degrees or greater than 2 pi radians? Sure. We could just rotate more than once. Like maybe you've watched figure skating or snowboarding competitions where they say they do like a 720 or a 900, right? Those are talking about rotations that are bigger than just one time around. Like for example, a 720 is 2 times around, right? And a 920, or excuse me, and a 900 is 2.5 times around a circle. So yeah, we can have an angle bigger than 360. That would just mean we go all the way around and then we keep going. And maybe we keep going, right? So yes, we can continue to rotate. So we can have angles that are bigger than 360 degrees or bigger than 2 pi. Okay, so that's going to help us today. Again, we're going to talk about things rotating and how that rotation then can move an object forward. Okay. All right, so we know a little bit about radian measure and the idea that one time around is 2 pi and that we can be larger than that. So let's look at what happens when a circle rotates. So I'm actually going to go to another page so I can look at that. Oops. So let's think about this. So here's my circle. So if I put a little point on my circle and I rotate that wheel around and I watch that little point move around my circle, not only does the point move, but it also creates an angle. So like, for example, if I were to stop my circle at that moment or stop my rotating at that moment, then I create an angle with where I started and where I am now. And maybe that angle's like, I don't know, 135 degrees, right? Or maybe it's smaller. But I could also go further around my circle and I would have a bigger angle, right? So as this point goes around my circle, it creates an angle. So let's talk about finding how much those angles are. So if I go 1 revolution around my circle, how much is that angle? So if my point goes all the way around once, well, how much is that angle? Maybe you might say 360 degrees if you're doing degrees, or you might say 2 pi radians, right? What if I went 10 revolutions around my circle? Well, then that would be either 360 times 10, or if I'm in radians, that would be 20 pi radians, right? And remember, this is saying radians is just radius lengths. So like 2 pi means I went 2 pi radius lengths around my circle, which is all the way. And 20 pi would be 20 pi radius lengths around your circle. That's how much that angle opens up, right? Okay. So we can relate how much we rotate to radians or angles. Okay. All right. Okay. So what is an example of rotating circles that we see all the time? Think of something you know that rotates. Maybe you said a wheel, right? That's probably one of the most common ones. It could be on a car, it could be on a bike. Maybe you said the hands of a clock rotate around, right? We have lots of examples of rotating rotating circles. Okay, so let's talk about specifically a vehicle. When a vehicle that has wheels travels down the street, there's a rotating wheel. And each time that wheel turns, it goes through a full revolution. So again, how many radians is a full revolution? Well, each revolution is 2 pi radians. So again, if I go 10, then I would go 20 pi. We were just talking about that, radians. So at the same time that this wheel rotates, it has contact with the street. So down here, I've got a little wheel, it's rotating. But when it's rotating, it's also contacting a street. And because it is, that wheel is moving forward, right? And it's going a distance. And it's going to cover a distance as it rotates those 10 times. So what sort of distance will it cover in the 10 times that it rotates? Well, let's think about one time. When this wheel rotates once around, then it's going to move along the street the same as the distance of the tire, right? So you can think of it as like however long it takes to get around would be how much it moved. Well, how long is that distance around a circle? A circumference. So each rotation or revolution would be a circumference. So if I rotated 10 times, then I would go 10 circumferences, right? That's one way of thinking of it. Or you could say I go 20 pi r. Interesting. Do you guys see this? 20 pi r and 20 pi radians? Just something to consider. So how about this? What if the wheel were bigger or smaller? Do you guys think that that would affect this distance it travels? Like if I had a smaller radius, do you think that would affect how far it goes? Oh yeah. If I had a much smaller circle, then if I rotated that 10 times, it's not going to go as far as the big wheel, right? So the radius makes a difference. Now, does that affect how many times we rotate? Well, if I tell you that they both rotated 10 times, if they both go 10 revolutions, then it doesn't matter how big it is because it would go the same number of revolutions, right? It's just the smaller one wouldn't travel as far. So the angular velocity really doesn't change as sorry, we haven't introduced that yet. The speed that you're rotating won't change regardless of how big your wheel is, but the distance you cover will change. Okay. All right. So this distance that we cover is sometimes called the arc length of a circle. Okay. And an easy way to think of arc length, and I'm going to go back to my other page. An easy way to think of arc length is to think of like if you had a string attached to your circle. And here's my little string. And as I went around the circle, I wrapped that string around the circle, right? And then I could measure that length, how long that string was. That's like arc length. Okay, we call arc length, in math, we typically call that S for arc length. Okay, so the arc length is really helpful because it's going to tell us how far we went, right? That would be the distance that we covered. So arc length is really important. So let's think about how we can calculate our arc length. Well, we can kind of get that in two different ways. What would we need to know to get the arc length? Well, we would need to know how many times we go around our circle, right? So we would need to know how many revolutions or rotations. Okay. And we would need how big the circle is, right? Our radius. Because again, we said that if our radius length changes, it's going to change how far we go. Okay. So let's say we knew how many revolutions we had. Okay. If we know how many revolutions we go around, you guys can help me figure out how far that would be. Each revolution, if we know the number of revolutions we go, what's the distance of a revolution? The distance around the circle once is how much? Is what in general? The circumference. So you could say it's the number of revolutions times 2 pi r. It's the number of revolutions times your circumference. That's one way to get arc length. Okay. But we could also use, we know radians relate length, right? Because remember, 1 radian is an angle that is opening 1 radius. So if you knew how many radians you rotated, right, the angle, then you could just take that. Each of those radians is a radius. So you could also just take the radius times the angle that you went, as long as, this is the important part, this angle has to be in radians. Remember, let me point that out one more time. When you're in radians, this literally tells you how many radii you go. So if this says, I went 2 pi over 3 radii, then I would say, well, then if I just take that times how long the radius is, then that's how far I traveled. Okay, so these are our two different ways. We can either take the number of revolutions times the circumference, or we can do radius length times radians. Okay, these two are the exact same thing. Okay, so that was me doing this. So here's our little formula. We have S equals R theta, or we can also use S equals circumference times the number of revolutions or the number of rotations. You can use either one. They both work. Okay, so let's keep going. So let's get to the big ideas for today. So if I have a rotating circle, that rotating circle has two speeds, guys, two speeds. What do I know about it? This rotating circle, it rotates at a certain speed, meaning it's going to have a certain amount of rotations per time, right? Like how fast it goes around in a circle. That's one speed. That's called angular velocity. And we use omega, the lowercase omega Greek symbol. It looks like a W basically, to denote that. And it's just the angle that you travel, so basically how much you rotate per time. And so let's think about that. That means that that could be in rotations per time. That could also be in radians, which is another way of doing an angle per time, or maybe it's even in like degrees per time. So angular velocity can be done in a bunch of different ways. And depending on what units you're in, if you're in rotations or revolutions or radians, you're going to have a slightly different looking value. It's kind of like the same idea of being in inches versus meters, things like that. Okay. Okay, so we have angular velocity, so how fast it's rotating around and around and around. But then once you put that wheel against a surface, right, then your wheel starts to move in a straight line. That's like your car moving, right? And so we have something called linear. Check it out. Line is that basic part. Linear velocity, meaning how fast you go in a straight line. So it's your distance per time. Angular is how fast you're rotating. So you have to have some kind of rotational part, meaning rotating rotations, radians, an angle, or degrees per time. And then your linear velocity, again, is how far you travel, which we just said that distance could be called arc length per time. So we could call that S over T. And we do this with a V for velocity, linear velocity. Okay, so this is telling me how fast my wheels are rotating, and then this determines how fast we go in how much distance we cover per time. Okay, so the big challenge is there a way that I can relate these two things? And if I know the angular, can I get the linear? And if I know the linear, can I go back to the angular? Well, this little relationship right here is going to help us do that. Okay, so if I know the angular velocity, which is theta over time, right? And I want linear. Well, let's look at what linear is. Linear is S over T. Well, we know that arc length could be replaced with R theta. Remember, this only works if it's radians because you're doing radians times radius length. So I could replace that. And then check this out, guys. If I bring that R out front, what is theta over T? Your angle over T? Yeah, it's angular. So if we take our angular velocity, now remember, to be able to do this, it has to be in radians per time. But if we take our angular velocity in radians per time times the radius, boom, we get the angular, or we get the linear velocity. This is really important that we pay attention to these different ways. So we have angular velocity is the easy one. Linear velocity can be done using this version. This is only if you're in radians per time, or what if I was in rotations per time, guys, then? Think about this, because remember, the reason we multiply by the radius here is because this part, the angular, is in radians. So that's why you multiply by how long the radius is, because each of these is how many radius did we go. If I do rotations per time, each rotation is how long again? Each rotation is a circumference, and the circumference is 2 pi r. So you can also do linear velocity by doing, if you have rotations per time, you can do circumference times angular. It just depends which angular velocity that you're in, right? Are you in chunks of the radius, which is why I multiplied by the radius, or are you in chunks of the full rotation, which is a circumference? Okay. So, all right, so let's look at some actual problems. Actually, I'm going to go ahead and just go to a new page and we'll do some problems together. So in a lot of these problems, we convert back and forth, we go from angular to linear and so on and so forth. So let's just get down to an example, and I think you guys will get a better feel for it when we do that. Okay, so let's say that we've got a bike and we've got our tires of our bike that touch the ground. That's my best bike today. And let's see, maybe the wheels on a bike are like let's say that they're 28 inches in diameter. And I will tell you, a lot of times when you're given real world problems, they give you the diameter because it's easier to measure the diameter of something than it is the radius. So let's say our wheels are 28 inches in diameter, which if it were me, I'd immediately go, okay, my radius is 14, just so I have that. And let's say that we know that our wheels are rotating RPM, right? Rotations per min, in case you're not familiar with that, right? Rotations per minute. Oops, let me make that a cloud. There we go. Rotations per minute. Okay, so let's say that we know that it's going, let's think, if it was a minute, maybe your wheels are rotating like 50 RPM, right? So they went around 50 times each minute. So that doesn't seem too crazy fast, right? Like it would take 50. I think that seems not too crazy. So, okay, so let's do a couple of things. Number one, let's get our linear velocity or our angular velocity. Angular velocity, well, technically, guys, we have how fast it's rotating. It's going 50 rotations per min. But maybe they don't want it in rotations per minute. What if they wanted it in rotations per second? Because sometimes I want it in something different. Well, that would mean we just have to convert this. So the conversion is actually pretty easy. If you think about it, I'm in rotations per min, but I want to be per second. So you're going to want to cancel out, you're going to multiply by a conversion. We're going to want to cancel minutes. So since minutes was on the bottom, we want to cancel minutes by multiplying by it on the top. And we want to go to seconds on the bottom. So see, I have to figure out a conversion between minutes and seconds. Does anybody know how many minutes there are per second, or like a relationship between minutes and seconds? I hope so. There are, in 1 minute, we have 60 seconds, right? Okay. So then if I multiply this, check it out, the minutes are going to cancel. And then I have 50 over 60, which reduces to 5/6. So I'd have 5/6 of a rotation every second. So almost a full rotation in a second. So that, I feel like speed-wise, that makes kind of sense. This doesn't seem like an absurd problem. Okay, so there's one thing. Okay. And maybe they want also the angular, but they want it in radians per min. Okay, I'm going to go back to this guy, which is already per min. How are we going to convert to radians? Well, if we know rotations, how many radians are in a rotation, guys? How many radians are in a rotation? One rotation. 2 pi. So you're going to convert, same way we did over here. We want to cancel out rotations, and we want to be in radians. So there are 2 pi radians or radius lengths for every one rotation. So most people are just like, oh, just multiply by 2 pi. I just want to show you how everything does reduce. Okay, oops, don't need that guy. So we end up with 100 pi radians per min. Okay, now here's the thing, guys. Every single one of these values, 50 rotations per min, 5/6 rotations per second, and 100 pi radians per min, those are all various versions of the angular velocity, right? It just depends what kind they want. So you might have to mess with it a little bit. All right, now let's get to the fun part, which is how fast are we going? Because that's really what we want to know, right? How fast is this bike moving? Okay, if I want to do that, I need the linear velocity. And okay, so let's go. We have 2 options here, right? If we remember from our previous, we can either do the circumference for rotations per time, because each time you rotate, you'll go with circumference. So that's one way we can get it. Or we can do the radius if we do radians per time. So it's our choice. So the nice thing is, because of the way I asked this question, we have a rotations per time and we have a radian. So we'll do both just to show how it works. Okay, so let's start with this one. If we know rotations per time, so 50 rotations per min, or sometimes this is written as revolution, so REV. So we have 50 rotations per minute times the circumference. And the circumference of this circle would be 2 pi r, which ends up being 28 pi. So each time it rotates, I go this much, the circumference. So then I could do 28 times 50. We'll just leave our answers in terms of pi. So 1,400 pi. And then this is in, technically you're saying you go 28, what are we, inches? Yeah, technically we go 28 inches in one rotation. So when you go from angular to linear, you should lose your rotations and be in a linear dimension like inches. So this is in inches per min. Okay. Okay, so there's that guy. Let's see if we had used our radian version. If we'd used our radian version, we would take our radius, which was only 14 inches. So technically it's 14 per one radius. I don't really write that, but I'm just showing you this first time, times your radian per minute. My radian per minute was 100 pi radians per min. And then check this out. We get 1400 pi inches per min, which we thought we should. We didn't think that that should change, right? So I can get it either way. So my thing would be if they started me in rotations, boom, I would just multiply by the circumference. If they started me in radians, then I would, boom, just multiply by a radius. Now, this doesn't really make sense because how many of you guys go, oh, I was going, even if I did 1400 times pi, so let me just do that real quick. So this is about, 4,398 inches per min. If I said that to someone, they would be like, what the heck are you talking about, right? We do miles per hour. So let's convert this to miles per hour. This is going to get pretty interesting. So I'm going to start with the 1400 pi inches per min, and I'm going to do it one at a time. Let's start with inches. First, I need to convert from inches to feet. So most of you know, I think, 1 foot for every 12 inches. Okay, but then I have to go from feet. Notice I'm always canceling. So feet on the bottom to miles. And it's 5,280, if you didn't know, per 1 mile. So if I did that, my inches would cancel, my feet would cancel, and I'd be in miles. Perfect. But now I want per hour, and I'm in per min. So all I have to do is cancel the mins. So the mins are on the bottom, so I'll cancel on the top, and I want to go to per hour. So how many minutes are in an hour? 60 to 1. Boom, boom. I'd be in hours. Now you just multiply straight across the top. So that'd be 1400 times 60 times pi. I'm going to just do the 1400 times 60 for now. So 84,000 pi over 12 times 5,280. 6,300 or 63,360. And again, I'm in miles per hour, which most people do mph. So now let's be real. We're going to want to multiply that out because that's crazy. Again, if you came up to me and said, I was going 84,000 pi over 63,360 miles per hour, I'd be like, thank you. I got nothing. And I'm a math teacher, right? So let's convert it to something useful. So I'm actually going to do 84,000 times pi, and then I'm going to divide it by that 60,360. Okay, now doesn't this just make you so happy? 4.16 miles per hour. Now that makes sense. I can think of someone going about 4 miles per hour. And I got to tell you guys, it's pretty slow. We're not going that fast. So just note to self, our bike, we must be just strolling along. Sorry about that. My thing went a little crazy. There we go. There's my cute, I think where's that from? That's Italy. Sorry. You get a little glimpse. Anyways, so that's that. Okay. So let's do one more because I can't help myself. Let's look at what if I knew how fast I was going and I wanted to figure out how quickly my wheels were rotating. And I'm just going to tell you guys, I'm recording this lesson and there's like a crazy storm kind of moving in. So if things get wild, I might pause the video. Just letting you know. This is I should figure out how fast the storm is moving. Anyways, I won't. Or how fast the winds are rotating, but I won't. Anyways, okay. So let's say this. Let's say that we know we have our bike. Let's be on our bike again. But this time let's actually know how fast we're going. Maybe we go by like one of those things that says, you're going 25 miles per hour, and it's a little sign on the side of the road. Okay, so we know we're going 25 miles per hour. And we know that our bike tires we'll keep them the same, 28 inches. Maybe we want to know, well, what's the RPM of our wheels, right? We want to know the rotations per minute. So basically, this miles per hour is a distance per time. So this is our angular. And we basically want to go back to this. Okay. So, well, let's think about this. First of all, we have two relationships that relate velocity and angular velocity. The first one is we can do r times omega if this is in radians per time, or we can do circumference times omega if we're in rotations per time. So here's my suggestion. If you want to go back to something that's already rotations or revolutions per time, then you might as well use the one that uses that. So like you could go to this one and then you'd have to convert from radians to rotations. I'm just going to use this one straight up. So, all right, let's set up our equation. We know the velocity is 25 and we know it's miles on top per hour. Equal to circumference. So I can get the circumference. This is the diameter, remember, so the radius was 14. So the circumference is 2 pi r, so 28 pi, and that is in inches. That's the units are really important here, times the angular. I'm going to leave it just a W for now, okay? Okay. And this is and technically, remember, this is going to, if I do this version, it's going to take me back to rotations. Okay, so the first thing I would do is probably divide by 28 pi inches, right? So I'd have 25 miles per hour. But instead of dividing, I'm just going to multiply by 1 over that because it just keeps all my units in a nice place. So right now, this is what I have. But this is a problem because this isn't in rotation per time. That's because you have two linear dimensions that need to cancel, but you don't have both in terms of miles or both in terms of inches. So we're going to have to connect those. So I'm going to start with the miles. So if I want to connect miles, I'd put miles here. I'm just going to go feet to miles because I know that one. 5,280 to 1. That would get rid of the miles, right? Okay. And then if I wanted to go from feet to inches, I'd have to divide to get rid of the feet, multiply to get rid of the inches, 12 to 1. But then look what happens. What? Both of them cancel? Yes, that's because remember, we were going from linear back to angular, so we should cancel. And technically, this was per one rotation. We just didn't write it in. So once you get all those linear dimensions to cancel, it's going to be in, guys, rotations per whatever time you have. And in this case, I'm in per hour. Okay. So at this point, I would be good if I wanted RPH, right? Which would be rotations per hour, but I don't. I want rotations per min. So I might as well just convert to min while I'm at it. So if I have hours on the bottom and minutes, or I'm sorry, hours on the bottom, I need to multiply by hours on top and minutes on bottom. So let's see, 60 minutes per 1 hour. Okay, now let's see where we're at. All my linear units drop, which put me into rotation because of my relationship, and I'm in per min. So my answer is going to be in rotations per min, or RPM. And let's see what we get. On top, I have 25 times 5,280 times 12. Ooh, it's a big number. 1,584,000 rotations per 28 times 60. Don't lose your pi. That's important. Pi. Now, again, if you came up to me and said this, I would say, what the heck does that mean? So let's go ahead and convert that out to a decimal. So let's see. That guy divided by, make sure you're using, when you put this into your calculator, you need a parentheses around that bottom. Otherwise, it's not going to be correct. So I got about 300.1 RPM. Woo! Those are some fast moving tires, right? But you see now why when we chose only 50 for our previous problem that we weren't really going that fast. Okay, so you're going to get some chance to practice this. I'm also going to expand on this in class. So we'll get to talk about it a little bit more, and I'm going to talk about some other relationships. So yeah, I'll see you in class.